Hello, everybody, and welcome to the 27th Meteorological Virtual Seminar organized by Ghana Meteorological Agency. This morning, we are going to be treating the topic on West African storms, drivers, trends, and future projections. And the one going to take us through is Dr. Cornelia Klein, who is with the UK Center for Ecology and Hydrology. Also, sorry. So we are going to be talking about the West African storms, drivers, trends, and future projection. And this is going to be chaired by Dr. Cornelia Klein, who is with the UK Center for Ecology and Hydrology. This morning, the topic we are going to treat is going to be on organized convective systems, which is also one of the dominant causes of rainfall and extreme events in West Africa. Also, Dr. Klein is also interested in convective storms, extreme weather, and how it affects the atmosphere with consequences pertaining to the regions and the water cycle. Her research is focused on tropical region in particular, with Africa and the South America. She's combined both sensing data and atmospheric modeling to evaluate convective and storm characteristics changing from decades and with time. Also, she's a NEC fellow investigating drivers of convective system organization and also a new way of predicting these powerful storms. Dr. Klein, you are welcome.
Thank you very much for the nice introduction.
You're welcome. Also, you can share your screen and start with the presentation.
Yeah. Try that. That all right for you?
Yes, please.
Okay, then I assume we can start. So, yeah, welcome everyone, and thank you very much for the opportunity to speak on this great platform. As was already said, so I'm a weather and climate researcher at the UK Center for Ecology and Hydrology, and I've been working on the topic of African rainfall and in particular organized convection over Africa for quite some years now. And today I'm just going to talk about quite a collection of topics and studies I've done. I mean, there should be many more names on this slide, many colleagues from different institutions, particularly in the UK and across Africa, that have contributed to this work that I'm going to present today. But there will be also a lot of background simply about what we know about West African storms and what drives them and what they are sensitive to now and I guess on the global warming context. So just to start, essentially with the challenges, as you will all know, we are facing across Africa, but particularly in West Africa today, because West Africa is so often and strongly affected by these very large organized storms, is the challenge that already today we see an intensification of convective rainfall. And in these images here, you just see an example of this very well-known storm, which occurred in 2019 and hit Ouagadougou, which was quite a storm in strength that you wouldn't necessarily expect within 100 years. And this had on the ground effects that were very, very extreme. But questions are around how often we might expect something like this in the future as global warming continues. But just thinking about the current state, already for the past, actually, we see that particularly extreme storms have intensified and become more frequent. So here in the bottom plot, left-hand side, you see a line plot based on rain gauge data, actually from Sahelian rain gauges. And this shows the contribution of extreme events to annual rainfall. And you see this has been continuously increasing from 15% to up to 25% since the 1980s to now. And on the right-hand side, you essentially see the same plot. The black line is the number of storms that has increased over the same time period. But now the red bars is actually collection from flood reports over that time. And you see that also the flood reports from different cities across the Sahel has increased, or this is specifically for Burkina Faso actually, but the reports on flooding have increased over the same time period. And now we can just say that this increase also in flood occurrence is surely a combination of population growth, water management in cities, also better information channels. There's just more reporting on flooding nowadays than there was in the past, but we do see this very clear trend in rainfall extremes already, which will affect sort of the frequency of flooding as well. Another challenge I'm gonna touch upon today is the effect of land use changes, which have also affected many regions across West Africa quite strongly. And these images here just show an example from Senegal, the Kaffrine area, where it's actually places that are very close by or closely together. But in the top, you see an agricultural field at the end of the dry season, so which essentially looks more or less like desert. There is nothing. Whilst here in the bottom where it says natural vegetation, that's a small shrubby forest, which people maintained in a village, which wasn't sort of an area that wasn't deforested and still is green even at the end of the dry season. And villagers say, for example, that they feel that in these areas, generally it's a bit cooler, but it's also protecting them from very strong winds from the desert. So they see certain benefits from actually keeping this natural vegetation alive in this region. And so we know that land use change can affect microclimates and rainfall distributions. And the question is, land use changes together with climate change is a big question, how that affects people in a warmer world, and also how it would affect rainfall patterns and water resources. So this is all questions we have in some way we work on at UKCEH. And just to give an example, how the land surface can actually affect land surface temperatures. So we really clearly see this in the satellite image here from MODIS Terra, where essentially purple and blue areas are cooler areas, which are forested in southern West Africa, whilst the greener areas are actually deforested. And so here you can see that in these pockets where there's still forest, land surface temperatures are way cooler than actually in the surroundings where forest was removed. And of course, this will affect, the atmosphere in some way or another, and also the people who live there. Then coming back to this overall question of organized convective systems. So just to, I'm sure most of you know something about this particular type of thunderstorm, but just to say a few words. So mesoscale convective systems are essentially very large thunderstorm clusters, and they are not only affecting West Africa, of course, they're very common across Africa, but in fact, they are the source of monsoon rainfall across the tropics, where they provide about 90% of the rainfall and produce about 80% of the extreme rain over land. And they are defined, it's a bit hand wavy, but they are defined as clusters that reach about 100 kilometers across, but very often they can grow much larger, and they are specifically what characterizes them is that these storms are very long-lived. So they don't only exist for an hour or two, but they can live on for 5-8 hours, and some storms can even survive over several days. And here in this bottom plot, you can just see in red and orange the regions globally that are actually strongly affected by MCSs. So these colors indicate the precipitation fraction that is contributed from MCS rainfall. And you can see that definitely West Africa stands out, but also Central Africa, you can see places in South America, but also across India and Southeast Asia, where the rainfall contribution from these thunderstorm clusters is particularly high. And so these regions have commonalities in how they are affected by these storms. So just thinking about the societal importance of these thunderstorm clusters, I guess the most important questions for people is how frequent these storms are and how intense. So essentially, they're thinking about now the weather time scale. So how frequent and intense are they nowadays? But what do we also have to expect for the future? And the reason for that is that, I mean, particularly in West Africa, most agriculture is still rain-fed. So there's a strong dependence on these rains, on these thunderstorms. So they are not only a danger, but they are also necessary because they provide most rainfall. If they are too infrequent, it can mean drought, it can mean food insecurity. But on the other hand, if we have too strong storms, that's linked to flood risks and rainfall extremes. So if these storms are too intense, they can produce flooding, which means damages to people, livestock, housing, and also disease risk, of course. So this is essentially why we're particularly interested or trying to better understand these storms and what drives them. So they're very high impact, as I just said here on the left-hand side. But the other side, or the problematic that we have at the moment, is that these MCSs have very low predictability. So even with the sort of state-of-the-art nowadays weather forecast models, we're doing very, very badly in trying to predict these storms on daily time scale, but even on hourly time scale. And that's mainly because our weather models, they are not able to properly predict the location and the timing of the storm. So when a storm is just 2 hours away from a city, our forecast models won't necessarily place the storm at that location. So it won't be able to tell us whether that storm will reach the city or not. So that's why our weather forecast models are sometimes not very helpful in telling us whether a storm is a risk or not. And then when we think about the climate timescale, so not thinking about days or hours, but rather thinking about the next decades, we have the problem that our global climate models, which usually operates at sort of horizontal resolutions of hundreds of kilometers, so they only see features that are larger than, say, 100, 200, 300 kilometers, they cannot properly see these thunderstorm clusters. So this is illustrated here in this grid, where essentially you see the outline and colors of a real storm as a satellite would see it, and the boxes indicate the grids of a global climate model. So you can see that the global climate model cannot see the small scale, the fine scale features of the storms, so they cannot really simulate them. And so this is still a problem that remains for us to say anything plausible or physically robust about how storms might actually change in the future. And this high impact, low predictability combination creates compound future risks due to the rainfall intensification that we already see and are expecting to continue in the future. We are also expecting more erratic storms and more droughts in between, so storms being more intense but potentially less frequent. And this combination creates a high adaptation uncertainty in general. So just a few words on how we actually detect MCSs. So how do we observe them? How do we monitor them? So we nowadays, so for the historical time, we're using mostly geostationary satellites and a few clever algorithms. So from satellites, you can essentially monitor clouds. I mean, many of you will know that and use it on a daily basis, but these data sets, they essentially give us cloud images on 50 to 30 minutes basis. And very soon we'll have 10-minutely updates of these images, and we can really follow the development of storms as they propagate across West Africa at a resolution of about 3 to 7 kilometers. And this is data sets that exist since the 1980s. So also looking back into historical data, we can do a lot with this to actually diagnose trends and how storms have changed in the past. And the information that we get from the satellite data is brightness temperatures, essentially. So it tells us something about how cold the cloud tops are. And the cloud top temperatures essentially are physically linked to some sort of rainfall potential in the clouds. So the colder the clouds, the more likely it is that they are actually raining very heavily. These white contours on the animation identify areas of the clouds that are particularly cold. And these are areas that are very active in the cloud. So in the storms, circulations, so very strong vertical updrafts, create these cold, very high cloud tops. And underneath these very high cold cloud tops, we essentially expect extreme rain. And this relationship between very high cold cloud tops and intense rainfall is just illustrated statistically here on the right-hand side in this plot from thousands of storms over West Africa, which were binned according to their minimum temperature within the cloud envelope. And you see the colder the cloud top temperature gets here, when you come to -80, you reach a probability for extreme rain of over 80%. And extreme rain in this case means something like over 30 millimeters per hour, which is based on the TRMM rainfall data set. So you can see that we can use these relationships to learn something about storms using satellite data purely. So we don't need to rely on models for historical analysis necessarily. But this talk is also supposed to bring you a little bit of insight on different drivers that we know about that are important to create storms, and the rainfall that these mesoscale convective systems produce. And this is just something that is illustrated in this schematic, essentially. So already in the previous slide, I was talking about these updrafts, circulations that exist in storms, and the strength of these circulations in some way affects the intensity of rainfall that storms can produce. And there's something like vertical changes in the winds that also affect how strong circulations in the storms actually get. And these are mechanisms that very locally affect how strong a storm gets and how much it intensifies. And these are essentially factors that we can analyze in the atmosphere. So things like atmospheric humidity, instability, wind shear, and radiation affect storm intensities in the atmosphere. But there's also factors on the surface that can affect how strong a storm gets, which is things like vegetation, the soil moisture states, the surface temperature, the surface albedo, and the turbulent surface fluxes. So these are essentially the very regional or local drivers that in the end create the intensity of a storm. But more thinking about a global perspective, which is also something that I know many people are interested in, is, for example, very large-scale circulation changes like ENSO will on a continental scale affect how strong storms might be in a particular year. But so in this talk, I'm primarily going to focus on these very regional and local drivers in the atmosphere and at the surface, to think about how this controls rainfall intensities, the storm circulation intensity, storm size, and so on. And so thinking a little bit further about what actually controls storm rainfall intensities, we're just coming to this kind of schematic. So when we want to know what the maximum rainfall intensity of a storm might be, just based on the conditions in which this storm develops, we essentially know that moisture in the air is a sort of the first order condition or the primary constraint on how much a storm can precipitate. That makes sense because the storm extracts moisture from the atmosphere, and that's the moisture that is essentially rained out. But there's other factors that we now know, and this is still all ongoing research actually, that can enhance this rainfall production, which is on the one hand vertical wind shear, so how the wind changes with height, which actually leads to the storm growing in size. It increases the moisture influx into the storm, and it reduces the amount of very dry air that is sucked into the storm from the surroundings, which would reduce rainfall intensities. So essentially the growth of a storm itself helps the storm to more efficiently produce rainfall. And this is also true for pure cloud aggregation. So when two storms exist side by side, over time, they might aggregate into a bigger storm with larger circulations. And again, these larger circulations actually allow the storm to increase the moisture input from the surroundings and to increase these circulations that draw in moisture like a vacuum cleaner, essentially, and to produce more rainfall. And so essentially, because on this slide, as you can see, it also says something. The problem with climate models in this context with these drivers is that climate models, given they can't resolve storms, they are not really taking into account, and nor do they take into account the effects of the land surface on the storm growth and this additional intensification. So essentially, what climate models can do is they can, to some degree, represent a storm response in response to moisture in the air, but they cannot represent all these two dynamical factors of storm growth. So there's a fundamental problem where we have a limited ability of climate models to represent storm physics at the moment. So, but now, first of all, coming back to the historical time, thinking about what has affected storm trends in the past. And there has been some major studies, particularly one major study in 2017 by Chris Taylor, my colleague, published in Nature, where we found that based on geostationary satellite data, the frequency of very large, cold, extreme Sahelian storms has actually tripled since the 1980s. And what we found that this was linked to an increase in temperatures in the Saharan desert, which increases temperature gradients across West Africa, going south to north. So the south-north gradient in temperature is getting stronger, which enhances wind shear over the Sahel, and thus actually lets storms grow larger and intensifies them. So what I was just talking about the effect of storm growth. And this is a sort of analysis that we've also done over southern West Africa, including obviously an effect on Ghana, where we similarly identified that this sort of differential warming that you see here on the map, so this is a temperature trend from era 5 since the 1980s. In this case, it is for springtime. You see that actually not only the Sahara is warming, but during springtime, even the Sahel is warming, creating very strong temperature gradients over southern West Africa, which actually increases wind shear over southern West Africa and intensifies storms there. And this goes also hand in hand with moisture increases over this region, increasing storm trends since the 1980s. And this is something just visualized in a little bit more detail on this slide, based on ERA 5 reanalysis data and GridSat, which is a satellite product, again, looking at storm brightness temperatures. And on the left-hand side, you see a Hofmöller plot where you just see monthly trends in temperature gradients. So this is the entire year. The colors in red is temperature gradients. It's actually temperature trends at these latitudes here, as you see on the y-axis. And going through the year, you can see that actually the northern parts of West Africa are warming more than the southern parts, and that this creates strong temperature gradients that reach southern Africa between February and April, and reach them again from October to November, approximately. And the contour lines that you see here in black are actually indicating wind shear trends that, as you can see, follow exactly this region of high temperature gradients. So what this is just telling you is that actually stronger temperature gradients between the south and the north of West Africa increase wind shear, produce wind shear trends, have produced them since the 1980s, which is affecting storm frequencies, which is illustrated here on the right-hand side. So in blue, these are significant storm frequency trends since the 1980s. So the darker the for the Sahel in the summer around August is actually also true for southern West Africa in the first and second rainy season. Although in this case, we have to say that wind shear is affecting this trend more in the first rainy season, whilst moisture trends, positive moisture trends, are affecting these storm trends more in the second rainy season. But this is just to say that actually we see these positive trends in storm frequencies across the whole of West Africa. It just depends on the season or the months you're looking at, and depending on the movement of the rain band, of the monsoonal rain band. And yeah, this is just looking a little bit closer into what I just said. So this is a correlation between storm frequencies and shear in black bars, and atmospheric moisture in blue bars. And this just indicates that wind shear controls storm changes more in the first rainy season, whilst moisture changes control storm changes more in the second rainy season in southern West Africa. Coming to another driver, so we're now talking about the importance of moisture for storm trends, of wind shear for storm trends, but the land can also drive rainfall change. And here I want to talk a little bit about coastal deforestation. So since actually the 1950s, but here I'm going to talk about since the 1980s, because data sets are a little bit hard to find going back to the 1950s. But there has been strong deforestation in the southern parts of West Africa. So where you see where it's green here in this map, essentially all this could be more or less relatively dense rainforest, but there has been a lot of sort of forest removal, but there are still where's dark green pockets of natural rainforest, you could say. But since 1975, as this map shows, the red bits have actually been further deforested. So essentially, forest has been removed in these areas, mostly for cocoa plantations, actually, but also partly just due to displacement, urbanization, and just the pressures from international trade. So, but the question is, if we change the landscape like this, would this also change rainfall anyway? And so what we did here is, so you could think about if you remove a forest, we already heard that might change temperatures, particularly it might increase temperatures. And to look at that, you can also use satellite data. And in this case, we used Meteosat satellite data to calculate trends since the 1990s, which is shown here in the red colors. So all the red colors actually indicate positive temperature trends in this coastal belt. But you see certain pockets that have stronger trends than other regions. And these essentially coincide with regions that have been deforested over that time period. And this is shown by similarly looking at satellite data for a vegetation optical depth, so VOD, which gives insights on plant leaf moisture, essentially, if you like. And when you correlate the land surface temperature trends with the vegetation optical depth trends over this period, you see a relatively nice correlation between these two. So between vegetation on the x-axis and land temperatures on the y-axis, saying that if vegetation decreases, essentially your temperatures increase, which is here in the top left, whilst higher vegetation moisture content means lower temperature trends. And so this is quite a clear relationship between these changes. And now we wanted to see whether this has in any way affected convection frequencies. And so for this, we used a data set where, again, from Meteosat, these geostationary satellites, where we identified convection areas over the past 30 years. And the result of this data set, the climatology of the diurnal cycle, is shown in this blue animation here. So here you can see the climatology of convective activity over the region. And what you can very clearly see as well is actually the development of the sea breeze over the day, over the diurnal cycle. So you see this almost following the coastline, this pattern that comes up in the afternoon, which is the sea breeze essentially moving inland. And so we can detect that this movement very clearly as well from the satellite data. And now we're looking at trends in these convection features, which is shown here in this right-hand side top plot. In red is positive trends. And okay, so this plot is a bit complicated. It's showing the hours of the day on the y-axis, and it's showing the relative increase in convection features on the x-axis as a function of distance from the coast. So the 0 here is the coastline, essentially, and it's sampling slices along the coast everywhere along the Gulf of Guinea. Essentially, is we took slices all across here where you see this convective band, and we composited it together for every hour of the day. And now you get an impression of trend changes as a function of distance from the coast in the sea breeze, essentially. And what you can see is that, so it's particularly red here in the afternoon. This is 15 or 1600 hours in the afternoon. It is particularly red, which indicates an increase in sea breeze convection of about 80% since the 1980s, about in this region, which is approximately 50 kilometers inland from the coast. But generally, it's all red. So you can see that the sea breeze has increased in frequency and is affecting quite a wide area, all the way up to about 100 kilometers inland. So we know the convection has changed. And we see, if you look at the panels here at the bottom, again, it's the same. On the x-axis, this is plotted as distance from the coastline. So here is 0, 50 kilometers inland, 100 kilometers inland. You see the land surface temperature trend from satellite data. So the trend is particularly high in this area where the sea breeze trend increased particularly. So in this black line, you see that there is a bump relatively close to the coast, which is directly coming from this enhanced deforestation close to the coastline. Which is shown here in the change in tree cover in these particular areas. So the solid line is what the tree cover used to be in the region in the past, and the crossed line is what it is, what it was in 2000. So we can see that particularly in this area, the forest cover has decreased quite a bit. And now what is just interesting is that this is also the region, as we know, there's many cities along the coastline where the population density has increased quite a bit. So we have a very, say, risky combination of increase in convection frequency, increase in temperatures in this area, but also increase in urban density and population density across the coastline that might create particular problems for cities in the vicinity of deforested areas. But this is something that would be interesting to look into a little bit more, how deforestation in particular urban areas interact and how that changes risks to populations there. So now you have seen that sort of warmer land can actually increase frequency of convection. I just wanted to say a few words more generally about how convective storms react to drier and warmer land, or what the statistics for that look like. So we can look at this not only thinking about deforestation, but generally about what happens if soils dry out, if they are warmer, if they are hotter, and how does that affect convection. And for that, we sampled convection in the afternoon from satellite data, and we looked at land surface states in the morning around noon at 12 o'clock to look at the soil moisture states before these storms occurred. And we split the storm samples into storms that occurred over wet soils and storms that occurred over dry soils. And the distributions for these different storm types are shown here on the left-hand side. So in the top where it says storm intensity, this is just showing the differences in cloud top temperatures of these storms. And the yellow line is the storms that occurred over dry soils, which, as you can see, tend to be colder than storms that occurred over the wet soils. So essentially, 25% of storms that occur over dry soils reach temperatures that are cooler than -80 degrees, so are very likely to produce extreme rain, while that's only 9% of storms that occur over wet soils. And when we now look at the bottom, which is looking at storm size, again, yellow line is over dry soils, we see that these storms are also about 40% bigger than storms that occurred over wet soils, which is just to tell you that even the surface conditions before a storm occurs can tell you something about the characteristics of that storm as it develops. And we looked into why that is. There is some atmospheric drivers that actually causes these differences in characteristics. So over dry soils, we see more moisture convergence. The air is also more unstable from surface heating, but also these drier soils drive strong temperature gradients, which can increase wind shear. And as I explained, wind shear can enhance the growth of storms. So these factors together actually contribute to the fact that storms tend to develop into something more intense than if they have to travel over wetter soils. And this is a relationship that is actually important or can be useful for early warning, and is something that we're starting to properly work on, actually. So the information from the land surface is really underexploited at the moment for storm forecasting and nowcasting, which is, as I said, very difficult. But from the land surface, we get a little bit more additional predictability. And the land surface we can observe in very high spatiotemporal frequency from the satellite data. So essentially what you see here on the left is a satellite image of soil moisture temperature anomalies on a given day, as an example day, which I chose because it's particularly beautiful. And the brown colors indicate the areas where the soils are hotter and drier. And the purple areas shows wetter areas of soils. And now from your current knowledge, you can perhaps think about where you think convection might develop on this day. And well, this is what the afternoon convection storm development actually looked like on this day, then on the same day. And you can see that this very large, actually well-organized clusters nicely developed along the dry soil boundaries and developed very strongly across these dry patches where they grew stronger and larger. And this is a behavior we see consistently over the region, not only over the Sahel, where land-atmosphere interactions are particularly strong, but as you can see, even over Southern Africa, this sort of behavior occurs. And this is work that's been done in the SWIFT project, which sort of aimed to improve storm nowcasting on our sort of more on the hourly timescales, where I know GMED have been doing a lot of work on trying to improve storm nowcasting on these timescales as well, and we continue to work together on that. Tools like this are actually now available on a UKCH nowcasting portal that was developed during that project and is constantly under further development. So if you're interested in any kind of storm observations or nowcasting, this is a great website to go to for storm monitoring. Just a very quick other example, just to move away slightly from West Africa. So this is actually over Zambia. A few weeks ago, I came back from a test bed, forecasting test bed with the Zambian Met Service. So it's similar things that have been going on in collaboration with West African meteorological services are now also happening with Met Services in Southern Africa. And just to say, or just to illustrate how strong the effect of the land surface can be, is again, it's just a very nice example. We had an organized storm here in the southwest of Zambia one day. You can see here the convective outlines is where the storm was particularly strong and rained a lot. And this is now on the following day, the land surface temperature anomalies. So where the colors are a bit lighter and white, it's where the storm rained on the previous day, and the browner colors just indicate much hotter, drier soils surrounding that area where the storm rained. And now I go forward time step by time step on that day, just to show you the convective development on the day following the storm. And so this is an hour later, and an hour later, and essentially what you can see is that convection on that day developed all around the storm patch, but where the soils were particularly wet, and therefore the boundary layer was particularly cool and shallow, we had no convective development. And this is even clearer when you zoom out a bit on that day. So here you see the storm patch. This is actually almost the whole of Zambia here, or the central and southwestern Zambia. There was a lot of scattered convection on that day, but where the storm had rained the previous day, you get no convection. And so you see there is some predictability in just the land surface patterns. And you can see that in other regions where there were rainfall streaks the previous day, like here in Zimbabwe, again, whereas lighter colors, there was rain the previous day, and there was no convective development on this day, but surrounding that in the warmer areas. So it's just to illustrate that not only the atmosphere tells us something about storms and convection, but also the surface state. So now, hard cut from just looking at observations and historical trends and observed storms to looking at the future and thinking about our models. So if we want to say something or know something about how storms might change in the future, we need climate models, obviously, to say something about future trends. But the question is, do we currently have the right tools? And there I was already hinting towards climate model problems that can't see storms. And I was now talking about the effects of land surface as well and the importance. And here I just wanted to highlight a study, again by Chris Taylor from 2012, where he looked at observations, or showed that in observations, afternoon rainfall globally is actually more likely to fall over drier soils. I think we have established that now, but the red colors here show you that rainfall is more likely in the afternoon over dry soils. When we now look at our climate models, same analysis, you see mostly blue colors, which just indicates that actually in our climate models, afternoon rainfall is much more likely over wet soils. So these climate models have the feedback sign with the land surface state the wrong way around, which is down to formulations in the convective parameterizations, and which just tells us that if we can't resolve the storms properly, we also get the response to the land surface wrong, which is a big problem, obviously. But even the more striking problem is what I already mentioned, is that our typical climate models, here illustrated in these two boxes again on the right, can't really represent the storm structures that we see in observations here on the most left-hand side plot. And between that is a whole range of scales, models at different resolutions. So you can parameterize storms at higher resolutions. So climate models are now being run at higher resolutions, but still parameterized. And the storms still don't look great. They are sort of like wonky polygons. Whilst we now also have entered an era of convection-permitting climate projections, where storms, as you can see here in this example, at 4 kilometers, look much more than the real storm here on the left, which we would observe in satellites. So essentially, we now slowly have tools with these convection-permitting climate models that simulate real storms, but they are very expensive to run. So we have only very, very few climate projections that actually resolve storms like this. And we have many, many, many simulations from climate models that resolve storms like this, but give us a better understanding of the uncertainty in the future, right? We can't use a single climate simulations from a very high resolution model to say anything about the future, because the future is uncertain. So we need to use many runs, many models to understand how uncertain the future actually is, to get this uncertainty spread. And so that's why actually we need the whole range of models, all the way from the high resolution climate models through to the low resolution climate models, because we get different things from these different types of models. From the high resolution models, we get the better storm representation. From the low resolution climate models, we get the model spread, the uncertainty range about the future. And so that's why actually there's a lot of work being done now to try to exploit these different strengths between the data sources that we have to learn something about the future. And so we now need to develop methodologies to bring these different data sources together. And so what I just said is essentially we can exploit the more realistic storm rainfall and more realistic land interactions from these high resolution climate models, and essentially combine them with the many simulations that we get from the low resolution climate models, because these low resolution models, whilst they don't represent good storms, they do represent plausible changes in wind shear, plausible changes in atmospheric moisture, and these are changes that ultimately affect how storms going to change in the future. So the large-scale states are good in the traditional climate models. It's just the high-resolution storms that don't work well. And so that's why, in this case, I won't go into detail on this slide too much, because maybe it's a bit too technical, but whoever is interested in sort of thinking about bringing together different kinds of future climate information, different climate models, can talk to me about it in more detail. But essentially, what we started doing now is learning something from the observations and the high resolution models about how storms react to moisture and wind shear changes, and bring that together with the moisture and wind shear changes as the CMIP models, the traditional climate models, would represent them in the future. And then via some statistical framework, which in the future could also include machine learning, actually, which would be a new and interesting avenue. We predicted new storm rainfall, you could say synthetic storm rainfall, from these CMIP models, from these coarse-scale CMIP models, that behave more like the high-resolution climate model storms. It's represented here in these box plots on the right-hand side. So this shows storm rainfall changes across the Sahel, as represented by the raw CMIP model output, which is the gray box. You see it's quite a large spread, and some models predict actually negative rainfall change in the Sahel for the time period around 2100. And this is for a high emission scenario. So this is RCP 8.5. Whilst when we use statistical methods to better represent the physical relationship of moisture, shear, and to these storms, which we did in the green case, you see that the extreme rainfall change is positive for all CMIP models, and is quite a bit higher, in fact, 25% higher than the raw CMIP models would actually produce. And we think this is because the CMIP models miss certain processes I was talking about, like storm growth, because they cannot represent it. But if we combine these different sources, we can better represent these physical mechanisms that are missing in climate models. And with that, I want to wrap up. So I think that was just, while topics going through storm drivers, trends, and future projections of West African storms. I hope we learned that in Southern West Africa, positive trends in storm frequency and rainfall are already visible from observational data since the 1980s. This is due to wind shear changes in the first and moisture changes in the second rainy seasons in Southern West Africa, as a consequence of global warming. But we also see that land heating from coastal deforestation contributes locally to convection increases. We also saw that storms get stronger when the land surface is warmer, and this land-based control on convection can be used to improve, as we can observe surface states in near real time.
Hello, Cornelia. Please,
Yeah.
we are working on the other interaction, so please you can continue.
Yeah. Okay. And then we heard that traditional climate models cannot see storms, but by combining the large number of existing climate projections with the new high-resolution climate models, we can produce more realistic future projections for rainfall. And essentially, just as a general note, climate projections tell us something about the future for planning on timescales of decades. And this is important for things like urban planning, like setting out drainage systems for crop breeding, things like that take a long time and that need to remain in place for very long periods of time. But actually, improved early warning systems for predicting storms on an hourly to daily time scale helps us for both for today's storms, but also for tomorrow's more intense storms. So in that sense, an impact-based nowcasting approach that better predicts storms on hourly to daily basis is also needed for climate change adaptation. So we need both of these essentially to be prepared for future storms as well. And with that, I'm happy to take questions.
All right, thank you very much for a very insightful presentation, which has taken us into the study of MCS. All right, Cornelia, before the questions come in, I would like to once again thank you and also open the floor for questions. If anybody has questions, they can ask. Oh, okay. So please, I would like to open the floor for questions. If anybody has a question, the person can ask. But before maybe somebody comes in, I have two questions I wanted to ask. So before you began, you were saying the MCS are conversing storm clusters which are greater than 10 kilometers. And I wanted to ask, what if they are lesser than 10 kilometers, but they have the impact, or let's say they cause an extreme impact over a specific area? Is the classification based on only how it spans, or it's also based on the impact it has on the area?
So the size, it's a common size of 100 kilometers across, actually. So these storms are 100 kilometers across where people start to talk about MCSs. But you're absolutely right in that it's a bit a hand-wavy definition and is not based on impact. So not every MCS has to be impactful. In fact, most MCSs are just can produce, rainfall that you would consider normal for thunderstorms. And as we all know, I mean, impact depends a lot on locality. Some regions of a city may be absolutely fine with, 10, 15 millimeters of rainfall, whilst already 10 millimeters of rainfall when soils are saturated or there has been rain for the last 5 days will produce heavy flooding. So in that sense, this storm definition is not based on impact. No, it's purely based on storm size.
Oh, okay. Thank you very much. And also, I wanted to find out if the mesoscale convective system, they are season dependent, and if so, does this cause an intensity based on the characteristics of a particular season?
Yeah, so that's right. So we do see that you get different characteristics, different MCS characteristics depending on the season. So for example, for Southern West African MCSs, we tend to see that the MCSs that you get very early in the season, actually just after sort of the, say starting in March, you tend to see larger, colder MCSs that are more driven by wind shear, so sort of wind changes, and that are more intense, actually, but less frequent in the first rainy season than in the second rainy season, where you usually get smaller storms, so smaller MCSs that are a little bit warmer, that tend to be a bit smaller, but they are much more frequent. So you do see this seasonality difference, which is specifically due to differences in atmospheric drivers during these two seasons. Yeah.
All right, thank you very much. Please, the floor is still open for questions. If anybody has a question, you can put it into the chat area. I read it out for answer, or you can raise your hands. I call you and you ask your questions.
Just getting my chat up.
Oh, all right, Dr. Klein, please, there's one question in the chat box. So the person is trying to ask, he wants to find out from you concerning the drivers of rainfall from direct scales ranging from the global level through to the local level. So from your presentation, these are physical drivers. So what about the social drivers?
Yeah, maybe I need to ask back. So what would be defined as a social driver, or is that related to anthropogenic drivers in general, something like burning of fossil fuels or deforestation, or social drivers like urbanization and bad urban planning, for example? But I guess then, yeah.
So I'm sure maybe we could take it from that perspective.
So, I mean, I guess, so I can just say, okay, starting with anthropogenic drivers more generally, which is not thinking about impact per se, but actually physical changes that are human induced. And that is essentially global warming, right? For example, but also things like deforestation. And the trends that we see in the Sahel and in southern West Africa are both ultimately linked to global warming on the one hand, because it is global warming what's actually strengthening the temperature gradients, which is what is increasing the temperatures over semi-arid regions and over the Sahara is actually an increase in atmospheric moisture. And this increase in atmospheric moisture just traps more heat in the atmosphere, particularly in very dry regions. So regions like the Saharas, regions like the Sahel, which are then warming up more than wetter regions. And this increases these temperature gradients, which then increases wind shear and feeds back on the storms. And then similarly, as I said, I mean, deforestation is clearly human-driven or social-driven, if you like, because it's happening because people needed that land for other things. But this is quite this is quite a different angle than thinking about the vulnerability side of things, where you will have huge differences in vulnerability depending on the region you're looking at. So, yeah, as I said, certain parts of the urban population will be much more vulnerable than, I don't know, some rural areas. You know, so obviously storm changes don't have the same impact everywhere. It entirely depends on local characteristics and local adaptation by the population.
Marshall, thank you. I'm sure Mr. Answer's question is answered. Please, we can move on. If others have questions, you can raise your hand, put it in the chat box. Okay, so, all right. Please, there are some few questions in the chat box, and I would like to read it out to you. So the first person is asking, can you explain the bits about the use of ML again, please?
The machine learning bit. Yeah.
Yeah.
Okay. So I can go into a little bit more detail on what the thinking here actually is, perhaps perhaps particularly thinking for now about the effect of moisture changes that we expect under global warming, atmospheric moisture changes, and how these changes might change storm rainfall. Already with that question, we have actually a big problem answering that with just using the traditional models, because as I say, they don't represent the storms. So we can use the high resolution model, climate model, to learn how, as moisture changes, how the storm rainfall changes. So you get a scaling, sort of a rainfall change by humidity change. And this kind of scaling you can use to scale a humidity change in the traditional climate model, essentially to predict some sort of storm rainfall change that you extracted from the convection-permitting model. So that would be a very simple linear equation. Rainfall change over humidity change times the humidity change in the traditional climate model. So we can use equations, very simple equations, to scale certain things if we know these equations and if these equations work well. And so where the machine learning essentially comes into play is that it might actually help us to to better learn these equations, which at the moment we can use simple linear equations to make these connections, but we know that in some ways, and including more drivers, not only moisture, but also wind shear, but also land, but all these effects that would change storm rainfall in the future, is something that that a machine learning algorithm can potentially learn from the convection permitting models. So the machine learning algorithm can learn how storms interact with the atmosphere and with the land now and in the future. And once the machine learning algorithm knows what the interaction is, we can use this system and essentially implement it for the traditional climate models and just feed the machine learning algorithm with the moisture changes, wind shear changes, land changes. And then this algorithm is hopefully going to tell us how the storm rainfall would change, taking into account all these drivers based on much more complicated equations that we don't know about at the moment. So the point here is that machine learning can probably really help us understand the ways, the underlying equations in which these storms interact with their environment. And it's something that which we can't formulate at the moment very well, and hence we can only very badly implement it in the traditional climate models. But this is an avenue that's, I think, currently quite a hot topic, to extract the interactions from high-resolution climate models to then put them back into the low-resolution climate models.
All right, thank you very much. So then from the Liberia Meteorological Services also trying to find out, can you explain the second bulletin points on the screen? So I'm sure this will deal with the summary points you give at the end of the slides. So he wanted a better explanation to the second point.
Yeah, so the first bit or the second bit, that storms get stronger when the land surface is warmer. Yeah. Well, so just about the first point, so storms get stronger when the land surface is warmer, simply because there's essentially more instability. Just coming back to my examples, where we can now, so geostationary satellites give us information about the land surface temperatures every, say, 10 to 15 minutes. So we can observe the state of the land surface continuously at quite a high resolution. So we see all these fine-scale features. And for a forecaster who's trying to predict a storm within the next hours, or for a forecaster that sees an existing storm and wants to say anything about where that storm might travel to or where it's going to intensify, this information about the land surface can be really useful, because when you see that the land surface is very dry ahead of the storm, you can at least assume with a little bit more certainty that that storm might survive and that it might intensify. And so in that sense, just the monitoring of the land surface state can help us to improve the early warning systems a bit more, because this information is not used at the moment at all. People don't look much at the land surface, even though there is information in the land surface state. And that's what that point tries to get across.
Thank you very much. All right, so Mr. Raphael is also trying to ask the role of pressure system and the level of formation of storms, since he didn't see it in the primary factors for the formation of storms.
The role of pressure systems, yeah, I mean, so it's true that, of course, synoptic variability does play a role when we have phases of convective activity and when we have phases where there's very little convective activity. So the storm drivers that I presented in this presentation are very much based on the assumption or the condition that the atmospheric conditions are already good to allow storm development. And what I'm more thinking about is, once you have a storm, and that storm may well exist because there is a nice trough traveling through, which helps the storm to actually develop. What are the atmospheric ingredients that might actually make the storm weaker or stronger. But I absolutely agree that, of course, the overall synoptic state of the atmosphere is sort of a larger scale baseline condition that might make convection more likely or less likely. So yes, but it's not indeed. So in this presentation, we weren't thinking about the effect of synoptic variability that much, because essentially it's just the variability of these drivers that I presented. More moisture, less moisture, more wind shear, less wind shear, that sort of thing. Yeah.
All right, thank you very much. So the last question in the chat box, great insight being shared by Dr. Klein. May I know what measures are being put in place to reduce the impacts of storms at both regional and global levels? Perhaps a concerted effort from various stakeholders could be effective, but how?
Yeah, I mean, that's a very nice question, and I guess leads a little bit away from my expertise personally, which is more like on the meteorological side. So I'm going to answer it more from the meteorological side. I mean, what I know is that globally and also regionally, there is now much more effort and understanding that at a minimum, we should put early warning systems in place for these storms so that people can prepare. If we're able to say that in a very strong, intense or extreme event is developing, might develop or is coming, and we see it and it's moving your way, that there is systems in place where we can send out warning messages and that people get used to react to these kinds of warnings. But I guess there's a lot of other adaptation measures that could be taken on the ground to just build more resilience to such storms. I mean, that starts with drainage, that starts with better urban planning. But I guess from my perspective, the work on better early warning systems is what I and my colleagues can mostly do, because that's where our expertise lies. And I know there is some global consent on that need now.
Sure, thank you very much. Please, if you have further questions, we can ask. Okay, so Steven is asking if the presentation. Okay, Mr. Steven, the presentation will be shared in, let's say, some few days' time. So if you were able to register for it, we are going to send you back a mail that is going to give you the link to the YouTube site so you can watch the video all over again. Thank you very much. All right, so please, if there are no further questions, I would like all of us to turn on our cameras so we can take a picture together before we end the seminar. So if we can all turn our cameras on, then at the count, we take our first pictures. All right, so please, on the count of 3, we take the first picture. 1, 2, 3. All right. 1, 2, 3. All right, thank you very much. Also, the next one will be in the next month, which is going to be the last Thursday of March. And I will entreat all of us that when the link is being shared for us to register, we register and also join. Also, the link will be shared to those that were able to register via email. And Dr. Klein, we thank you very much. We are really appreciative that you were able to spend your time with us and take us through MCS and storms over West Africa. Thank you very much, and thanks to everybody that was able to join.
Thank you all.
All right, and also the next month, Ghana Meteorological Agency is going to celebrate their Meteorological Awareness Month, which will entreat everybody should also pay attention or log on to. Thank you very much.
Thank you.